This is Nanoscape. I'm Seth Zimmerman.
And I'm Erin Spain.
On this show, we venture into the frontier of nanotechnology
With experts in the field who are turning the science of small into the next industrial revolution.
This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Today's guest, Jarad Mason, is a scientist, inventor, and an alum of Chad Merkin's group here at Northwestern, who has been called a force to be reckoned with in the inorganic materials world.
He is an assistant professor in the Department of Chemistry and Chemical Biology at Harvard University, where his research group applies the tools of synthetic chemistry and nanoscience to design materials that address basic science challenges in energy, sustainability, and medicine.
We are thrilled to have him on the show today to talk about his work with nanoscience and porous materials, including innovations in gas transport that could improve medical treatments and energy systems, as well as advances in sustainable materials that aim to address global challenges. Welcome to the show, Jarad.
Thanks for having me. It's a pleasure to be here.
So as we mentioned, before joining the faculty at Harvard in 2018, you were here at Northwestern. So what initially sparked your interest in nanoscience as a student and later brought you to Chad Merkin's lab as a postdoc?
Yeah, I did my PhD at University of California in Berkeley, where I focused mostly on materials chemistry research and was designing materials for separating gases and storing gases, applications like carbon dioxide capture, hydrogen storage, methane storage for vehicles, and never really had any exposure to nanomaterials synthesis or characterization, but it was something that I thought was important and something I wanted to be part of future research that I would hope to conduct as an independent investigator. And so I was looking for postdoc opportunities where I could learn more about nanoscience, and Chad's lab at Northwestern provided kind of an ideal setting for me to be able to do that.
Well, let's dig into your research a little bit. It really spans different fields, but porous materials are at the heart of much of your work. So first, tell us about your lab. And for our listeners who may not be familiar, can you explain what porous materials are and why they are important in the relevance of nanoscience?
Yeah, my research group is very much a materials chemistry research group. So we like to think about ways of designing and studying materials to address both basic science and applied challenges. We work across a wide range of different types of materials. We're usually less interested in specific types of materials than in using materials to kind of solve problems. And porosity or porous materials happens to be one class of materials that's often really helpful for solving what we think are really important problems. And so a porous material is a material that you can kind of think of as having tiny nano-sized holes throughout the material. And so we typically work with crystalline or ordered porous materials where you can imagine something kind of like a honeycomb type structure where you have voids interdispersed throughout a kind of ordered network. And when you take holes and you put them in a material and you make those holes really small, all the way down to the nanoscale and even smaller than a nanometer, you can get really high internal surface areas. You have huge amounts of surfaces in a really tiny volume. And so you can make porous materials that have surface area that is equivalent to an entire football field in just basically a milliliter or close to half a teaspoon of a material. And so that's a huge amount of surface that can interact with different species, like things like gases. And if those gases have any kind of sticky interaction for those surfaces, that allows you to concentrate the gas to a really high density within those materials. And so you can kind of create these well-defined, judiciously designed environments for carrying out chemical reactions, for storing gases, for separating different species. That's one of the reasons why we really like porous materials, and we think they're a really powerful class of materials for addressing a lot of challenges.
Organ transplantation is often a race against time, with preservation being one of the biggest hurdles. And your research is exploring using nanoparticle-loaded water to extend organ viability, which sounds crazy, but what makes this approach so promising, and how do you envision it impacting the future of medicine?
Yeah, this kind of highlights one of the research directions that we've been exploring, leveraging the properties of porous materials to address important challenges. And the challenge that you've kind of alluded to in the context of organ transplantation is really fundamentally, at least in part, a gas solubility challenge. And so we got very interested in the challenge associated with being able to store or transport gases efficiently in water, because water is a very strongly associated solvent. Water molecules really like to stick to themselves, and they don't like to move apart to make space for gas molecules. And so gas solubilities are really low in water. This is particularly a problem for biology and for a lot of biomedical technologies, including organ preservation, because oxygen solubility in water is really low under normal kind of conditions. That's why we have red blood cells in our body, and red blood cells are packed full of hemoglobin. They don't contain any other organelles or a nucleus or anything like that. They just contain hemoglobin so that you can pack enough oxygen molecules into a small enough space so that you can get oxygen efficiently to your cells and tissues and stay alive. The problem is when you take an organ out of the body, you're no longer in blood, or the organ no longer has access to blood, and you're typically suspending it in kind of a saline solution. And so the density of oxygen in that solution is about 40 times less than the density of oxygen in blood. And so your organ typically becomes hypoxic under those conditions, which is just a fancy word for saying oxygen deprived. It can't get enough oxygen. And so that's one of the reasons why you have a kind of short amount of time to transplant an organ before its quality deteriorates. And so my group has developed porous nanomaterials that are capable of storing gases like oxygen at really high densities. We basically make the pores of our materials relatively hydrophobic so that liquid water doesn't go into them. And we are able to design the external surface in a way that these materials can be really biocompatible and also really easily dispersed within an aqueous environment or any kind of water solution. And so we make solutions that look kind of like water, but they have empty space inside them, and that empty space is filled with gas molecules. And so we can add in less than 4 volume% of our porous nanomaterials. So you have a solution that's 96% water, but it has the same oxygen carrying capacity as blood. So we've been looking at how we can use those nanomaterial-based fluids, which we refer to as microporous water because of this porosity that we're effectively incorporating into a water-based solution, as kind of like an artificial blood substitute, where we can use it for storing organs or perfusing through organs when they're outside of the body and don't have access to the normal biological mechanisms for transporting blood. And we've been able to show in some animal studies that this can significantly improve the quality of the organ after it's stored. And so we're excited to see how far we can push this and what implications it might have for organ preservation.
How long does an organ usually last or survive currently, and how long have you been able to increase that time?
Yeah, it depends a lot on the organ. So organs like livers, I think you have around 12 to 24 hours before they need to be transplanted. It's the second most commonly transplanted organ. Something like a kidney, which is the most commonly transplanted organ, I think you have closer to 1 to 3 days. Other organs can be even shorter amounts of time, as few as 4 to 6 hours, depending on the specific organ. We established a collaboration at Mass General Hospital here with a group that's really a leader in organ preservation technologies. And so with them, we've been able to do a series of both in vitro experiments and ex vivo experiments, meaning we basically use a rat model or rats and kind of do a simulated transplantation surgery. So most of our studies have been with rat livers so far, but I think that highlights one of the really great things about doing research here at Harvard and in the Boston area is having access to a really top-notch medical school and groups that are really great to collaborate with, which is a very similar situation to what I encountered at Northwestern in the Chicago area, where there's really great opportunities for collaborating at the medical school to allow us to do kind of animal studies and things like that that really wouldn't be possible for us to do in our own lab.
This could really be a game changer in the world of organ transplantation. Can you talk about that? What this could mean for these surgeons and patients, families?
Yeah, I think this is, kind of one potential tool in technology that could offer opportunities for really being able to extend the time over which you have to transplant an organ. If you can really store an organ more in blood effectively than in water so that it's in an environment that's more similar to its native state, I think that has a lot of potential for being able to open up new possibilities for better matching donor organs to recipients that need them and improving outcomes after transplantation surgery. That's certainly not the entire solution, but I think it has hopefully a role to play this and other types of technologies that people are exploring to improve organ transplantation outcomes. The organ transplantation field is a really difficult field. It's kind of very heavily fragmented, and it's a very risk-averse field as well. And so there's a lot that one kind of needs to do to really prove a technology works and is safe and can be used, particularly in an area like this. And so that's one of the things we're excited to see, kind of how far we can push.
So when we think about organ transplantation, I think of those igloo coolers that say like human organ, right? And so what you're talking about is the material, the solution that the organ would be in would be like in that cooler, just replacing the saline that is currently being used. It would be replaced with this new solution that you've helped to create. Is that right?
That's exactly right. That's one of the approaches we're looking at, is just replacing the solution and see how much of a benefit we can have there. People are also exploring more advanced technologies where you actively perfuse or move a solution through an organ, kind of like we circulate blood.
Like injecting it into the organ?
Injecting it, exactly. Okay. Kind of like maintaining flow of a fluid through the organ, just like your circulatory system does when it's inside the body. But there's a lot of challenges associated with using blood for that, and concerns about diseases and things like that. And so having a artificial blood substitute as your fluid that you're circulating offers potential benefits. And so we're kind of exploring both this passive, conventional, static storage in an effective saline solution, as well as this more active perfusion-based technology that several other research groups have been developing.
Obviously, you're not afraid of challenges here. What made you decide to work on a project like this that, has a lot of challenges? You're working with potentially human organs in the future, these biomedical applications. Are they going to be safe and compatible for humans? What made you want to pursue the medical side of your work?
Initially, we were interested in fundamental research questions and basic science questions. And the basic science question we were interested in this particular case was, how do we develop materials? At least initially, we converged upon nanomaterials, but materials that could effectively and efficiently transport gases in water. And we knew that there were biological applications potentially where a new solution or approach to doing this could be relevant, but we really weren't kind of going after those initially, more this kind of fundamental materials chemistry challenge. But I've always really liked working on research problems where we have some interesting basic science questions. How do you do this at a molecular level, and how do you develop synthetic chemistry strategies to address a particular challenge? And then once we have a solution or an approach or a material that seems like it's really working, to be able to simultaneously push both our basic science knowledge of that particular materials platform, establish new structure-property relationships, but also to push the materials forward from a translational perspective, or to really target actual applications. For one, so that we can try to have an impact in a particular area, but also trying to actually implement our materials in real applications better informs us about what the kind of most important challenges are that we should try to address at a chemical level. And I think that's something I really learned both from my PhD advisor, Jeff Long at UC Berkeley, and also Chad's lab, and Chad himself, and being not afraid to push things in new directions and try to take things beyond just initial kind of synthesis of a new material and structure property relationships, but really trying to actually implement them in different areas. And so we've been fortunate to be able to do that in a biomedical context for these particular materials and work with some really great collaborators, as well as bringing in really talented students and postdocs that have expertise that I don't have, so that we can actually explore some of these things.
Well, let's jump from nanomedicine to one of the other branches that you're working on, and that's energy and sustainability. So people have heard of Freon, but they may not realize it's contributing to some environmental issues, let's say. You're working on a solid refrigerant that could be, let's call it, a game changer for cooling technology. What makes Freon outdated, and how does your approach offer a better solution?
Freon is a challenge mostly from an environmental perspective. So Freon is a gas, it's a fluorinated gas, part of a broader type of gases, fluorocarbon-based refrigerants that are present in pretty much every air conditioner, refrigerator, or heat pump that's in use around the world. And we pump heat or we cool devices like the inside of your fridge or your home by basically evaporating and condensing that fluorocarbon refrigerant or Freon. Those refrigerants are problematic because they have a lot of carbon-fluorine bonds, and carbon-fluorine bonds, even if you don't know anything about chemistry, they're really good at absorbing infrared radiation in the upper atmosphere and reflecting it back down to Earth's surface, actually much better than carbon dioxide. And so they have global warming potentials that are a few orders of magnitude higher than carbon dioxide because of that. And so even though most vapor compression systems, which underpin all of our refrigerators and air conditioners, are kind of closed-loop systems, it's basically impossible to make them leak-free, at least in any kind of commercially viable device. And so these fluorocarbon refrigerants leak into the atmosphere to a surprising extent. And right now, direct emissions of fluorocarbon refrigerants are responsible for about the same amount of greenhouse gas contributions as the entire aviation industry.
Whoa.
So it's a really huge impact on the environment. And so they're increasingly being regulated and banned throughout the world. And so there's a really big push to either identify more sustainable volatile refrigerants, to explore alternative cooling and heating technologies that don't rely on having to use a fluorocarbon refrigerant.
So where has your research gone so far in the sort of fight against Freon?
Yeah, so we've been exploring basically an alternative approach to heating and cooling that functions very much like existing vapor compression systems, but that does not rely on a volatile refrigerant. And so we've actually been working on what is known as a kind of solid refrigerant, or the more fancy word for this is a barocaloric material, which basically just means pressure-induced thermal change. Baro for pressure, caloric for heat. So if you apply pressure to a material, and it heats up, and you remove pressure and it cools down. And if you can get it to heat up a lot and cool down a lot, then you've effectively made a refrigerant. The challenge, though, with doing this with a solid is that most solids are not nearly as compressible as a gas, and it's really hard to induce large changes in temperature in a solid material like you get when you take a Freon-like refrigerant and condense it into a gas or evaporate it into a liquid, where you can get really large changes in temperature. And so for most solid materials, even if you apply several thousand atmospheres of pressure, you get only modest changes in temperature. If you think about the difference in temperature between, say, like the inside of your fridge and behind your fridge, you generally need at least 20 to 30 degrees Celsius in order to make something that's a practical refrigerant. And so my research group became interested in kind of what's really a materials chemistry challenge. How do we think about designing solid materials where you can induce really large changes in temperature, ideally comparable to what you get with a fluorocarbon refrigerant, relatively modest pressures, ideally pressures that are similar to those that we already use in vapor compression systems, which are on the order of 20 to 30 atmospheres. And so we've designed several new classes of solid materials, mostly phase change materials, or materials that undergo pressure-induced phase transitions, where we can get very large changes in temperature at relatively small pressures. And we've been trying to understand and manipulate these phase transitions and also leverage these materials in actual devices to show how we can create more solid refrigerant-based heat pumps and cooling devices.
Obviously, there's a lot of industries that would be very interested in this. And, you could probably work for a major corporation helping them develop this type of work, but you've chosen academia as your career. Can you talk a little bit about that? Why did you choose to go the route of working at a university, running your own lab, instead of working directly for a corporation in an industry, helping them find the next big thing? What drove you to academia?
Yeah, I think one of the most attractive things about academia is kind of the flexibility and freedom that we have, which actually doesn't necessarily constrain us entirely to working within the realm of academia, but can allow us to do things like start new companies. So I had a graduate student and postdoc actually who were working on this solid refrigerant-based product. I got really interested in translational opportunities and formed a startup company with me a year or so ago, and they've been working to build kind of prototype systems. And so I think academia is a unique job or career where we have the freedom to participate in those types of ventures, not in a full-time way, but at least in some kind of meaningful way. And, we can interact with companies either through consulting arrangements or through direct collaborations to either help companies develop technologies or to license our technologies to larger companies as well, or to collaboratively try to do research that can move technologies forward. But I think just more broadly, in an academic lab, you kind of have the freedom to pursue whatever research questions and scientific challenges you think are most interesting and important. And in some cases, those can be very fundamental and basic kind of science or chemistry questions. And in other cases, they can be very applied, and you can kind of pursue multiple research directions simultaneously. You can shift your focus over time. You can craft your group to be kind of whatever you want in terms of both size and the types of students that you bring in and the expertise that they have. And then perhaps most importantly, you get to work with extremely talented students and postdocs who can push research in unexpected directions and bring in their own ideas, and can take ideas I have that are poorly formed or not super well thought out and turn them into really good ideas and interesting research directions. And I think that's one of the really rewarding parts of our job and one of the most fun parts of our job.
So you mentioned you did a startup last year, and I'm always interested in this relationship between the two worlds of academia and industry. And how would you say, is it evolving in any sort of way in the last, let's say, decade? And where do you think it's going, and how is it going to apply this relationship, of nanoscience and the real world problems that we're facing?
Yeah, I would say there's a very synergistic relationship between industry, whether it's a startup environment or more established company in academia, where there's multiple paths to translate technologies from an academic lab into a more commercial environment. I think, in an academic lab, we have the freedom to pursue whatever we think is interesting from a purely academic or scientific perspective. And we have the time and generally resources to dive deep into, fundamental questions, which is not just important from the perspective of advancing our scientific knowledge, but often informs the design of better materials or teaches us how to address challenges in new ways, or to make materials that have access to functions that we weren't able to achieve previously. And that doesn't always happen in a very rational and predictable way, but often sometimes through just pursuing new knowledge do we make those kind of discoveries. And that's something that's really challenging to do in a more corporate environment, where you're much more focused on translating the technology into something that's commercially viable and having a pretty narrow path to follow there, or at least less freedom to maneuver. It's not to say that discoveries can't happen that are unexpected along that way, but I think much more focused on really scaling up or demonstrating that something really works and making it commercially viable, and economics, and business strategy factor into all of that. But I think, companies are able to often push things down the commercialization or translational pathway a lot faster than we can in an academic environment. And so I think there's synergistic relationship between both. And then as you try to push things down the commercialization pathway, you often identify unexpected challenges with the technology, and that can motivate the need for further fundamental research in some cases that a company might not necessarily be able to take on themselves, but that an academic lab might be better suited to. There's kind of a natural relationship between those two environments.
Is there like a specific point, like when you're doing your research, like, okay, I've taken this as far as I can take it in academia, and now it's time to take it to industry? Is there any like kind of benchmark or specific point in your research, like, okay, that's it, we've taken it as far as we can go?
It's a little bit case specific, and it's not always so clear cut, but I think, in our case, for example, for the solid refrigerant situation, we started building prototype devices in my lab and, thinking about heat exchangers and all these kinds of things. And it was getting to a point where, unless we were to hire a bunch of like mechanical engineers, like it was kind of far away from the expertise of my group, and it made sense to kind of push that in a different environment. But you also have to have the kind of people that want to do that. In the case of a startup company or interactions with another company, there has to be convergence of both the right opportunity, right group of people, and also to be far enough down the technology development track that you de-risked certain aspects of the technology in your lab so that there's kind of a clear path forward in a company setting. So depending on the nature of the technology, I think that can be different, for like development of pharmaceuticals, for example, or like small molecule drugs. I think that's been very clearly established, more or less, with clinical trial pathway and timeline, at what point it makes sense to do different things. And the like more tough tech, clean energy technology sector, it's not always as clear cut, and there's multiple options for when it makes sense to move a technology out of the lab and into a company. But that doesn't mean we stop doing research that's related to that technology either, and things can kind of continue to move forward in some cases in parallel.
You've done so much since leaving Northwestern as a postdoc in Dr. Merkin's lab. And really, there's a lot ahead. I mean, you're still very early on in your career. Tell me about the next 5 to 10 years. Where would you like to see your research having the greatest impact?
Yeah, I think right now we're particularly excited about really kind of two main directions. One is continuing to push forward the development of new thermal materials that can address challenges related to heating and cooling technologies, and exploring really different approaches beyond what we've already done to really push the boundaries of what's possible with these materials and developing new sustainable heating and cooling technologies. We're also really excited to push deeper into biomedical applications related to our oxygen transporting nanomaterials, and looking forward to doing some actual in vivo experiments, as well as thinking about other areas in which we can have an impact on addressing gas transport challenges, including things like bioreactors, where getting oxygen efficiently into a bioreactor when you have cells that are producing therapeutics, or also things like biofuels, can be really challenging for a variety of reasons. And so having an impact in that space is something that we're really hoping to do in the next few years. But I think one of the nice things about academic research is you don't necessarily know exactly where we'll be in 10 years, and it can easily be unexpected discoveries along the way or new ideas that get us really excited and push us in directions that we didn't fully anticipate. But hopefully we'll be working on interesting scientific questions and impactful problems come that time.
What motivates you, though, to keep pushing these boundaries in nanoscience? Because as Aaron said, you just keep going, but how? Like, what keeps you going?
I think a combination of things. We're motivated by interesting scientific questions and trying to find answers to them, a general kind of pursuit of knowledge. We're also like to try to solve problems. And so anytime that we think there's a problem that our expertise in synthetic chemistry, nanoscience, materials chemistry can really help address, we're interested in seeing if we can generally design materials to address that challenge. And so trying to solve problems, trying to answer questions, things that are very motivating. And, I'm very fortunate that I don't have to do a lot of this all by myself, but I'm working with really talented students and postdocs. And so watching them learn and really drive their research forward and seeing them grow as independent scientists is something that makes it actually very easy to do my job.
Nanoscience has been called a quiet revolution, and I just love that term. So working at the molecular level is to make these big changes. Do you think the public fully understands its potential?
Yeah, I don't know if the public fully understands their potential. I think there's a lot of buzz around the word nano and a lot of images that brings to mind for different people, some of which may be accurate and some of which may be not accurate. But I think we could probably do a better job of communicating the potential that nanotechnology has to impact people's health and lives and the technology that they use in really beneficial ways and why that is.
Is there anything you want to put to rest right now? Any kind of assumption or anything out there the public is thinking that you just mentioned? Like, no, that's not real. Just stop imagining it. Stop thinking it's real.
I don't know if there's anything universally kind of accepted, but I think there's probably concerns over like nanoparticles being toxic or bad for you. And I would just say that that's certainly not something that's universally true. Just like it's difficult to say, that all types of some type of food are universally bad for you, and that everything has very different kind of properties, behavior, and it's very much dependent on the specific nanomaterial that you're considering.
Is there any kind of application that in medicine or energy that maybe the other direction people aren't talking enough about, that maybe they do know, but this is it, and people should really be paying a lot more attention to it?
I mean, maybe it's underappreciated, the role of nanotechnology already in some medical applications, like COVID vaccines, for example. The initial RNA vaccines were basically housed in what are effectively lipid nanoparticles. And that's already an example of nanotechnology played a role in vaccine delivery that had a huge impact on the world, and not usually framed as like a nanoparticle technology, more as like an RNA technology, which it is. But nanoscience certainly plays a big role in allowing that technology to function as intended.
Jarad, thank you so much for coming on the show. We're excited to see what happens next with your research.
Thanks for having me.
Thanks so much for listening. This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Be sure to follow this show on Apple Podcasts or wherever you listen to podcasts, and be sure to give us a 5-star review.
For more information about IIN, go to our website, iinano.org/podcast.